Hello, in this video I will show you what torque is and how to find torque. So let's just assume we have this object and it could be just a cardboard cutout. So we'll pin the cardboard cutout on the corkboard at this O here. We can call this O axis of rotation. Or AOR. So the this piece is basically free to rotate around that point, and in order to make the rotation happen, we'll apply a force. So let's apply a force here. So we'll maybe just poke a hole and put a string through so we can pull. So here's the force, F1. Okay. So since the force is pulling, we can imagine what happened with this piece. It's going to rotate, right? This side is going to rotate up. We don't have to imagine the whole situation where we keep pulling. Maybe the string will actually stretch and will start tugging against this object to prevent it from rotating. But we're just talking about this moment. At this moment, the string is going to rotate this piece, this cardboard cutout. So the effect of applying a force that causes an object to start rotating or increasing or decreasing its angular velocity, this effect is caused by a torque. It's not exactly just the force, but also where the force is applied. Let's imagine if we just put a string here at this O and we try to pull, we wouldn't be able to rotate at all. So this is just like opening a door. And the O is the hinge, and this point here, let's call this A, and this A is the handle. So you can easily open the door just by pulling the handle or pushing the handle, and only very little small kids who don't really know any better would push maybe the middle of the door, try to cause it to open or close. It's not effective, as adults already know that. So the torque that this force causes is related to the force itself and also where it is applied. So let's do some definitions here. If I extend this force, just try to draw an infinite line through this force in both directions. And this line is normally called line of action. Okay, so now we have this line, and we also have this point. We can draw a perpendicular line between the point and this line of action. So it'll be this, right? So perpendicular between line of action and axis of rotation. Okay, axis of rotation and line of action. And this length, we call it L for lever arm. Okay, so lever arm L. And the force is applied at this point here. Although the lever arm doesn't really connect the axis of rotation to the point, it usually does not. This is where the force is applied. So the lever arm is related to the line of action and also the axis of rotation. Remember this perpendicular distance. So now we can define torque. Torque T or tau. So torque is equal to the force times the line of action. So if we have a force F1 and the line of action L1, and maybe we can also have other forces, F2 and L2, and we can have a net torque. So what the torque does is it affects the rotational motion. It's causing angular acceleration. So this force here that pulls and causes this cutout to rotate in this direction we call it counterclockwise, right? A counterclockwise rotation, or the torque that causes this, well, we would call it positive. So you can also use your right hand to try to follow the rotation with your 4 fingers. And if you see there's a counterclockwise rotation, then it is a positive torque. So the torque sign, so positive for counterclockwise rotation and negative for clockwise rotation. This is just ignore the other forces, what the other forces would do, and just imagine this one force with its own torque. Which way does this torque cause rotation if the object was at rest? So that's my idea how to find out the rotation. So in this case, we have a counterclockwise or positive torque. All right. So now let's calculate. So we have torque equals force and lever arm. So what exactly is this lever arm in terms of other quantities we could mark on the diagram? So we have this quantity here that goes from the axis rotation to this point A, or the OA or AOR to A. So this is going to go through the letter L there. That's unfortunate. So let's see if I can erase a little bit. Okay, so this from axis rotation to this point where the force is applied, you can draw this vector, and this vector you can call it vector R. So the vector R is related to the lever arm, and let's extend this vector. We have the angle between this vector and the force vector. We can move this vector over here if we want, because moving the vector does not change the vector. So it'll be the angle between the R and the F. All right. So let's draw a separate and slightly bigger diagram for illustration. So we have this. Alright, so this is AOR. This is that point A where the force is applied. And this vector is R. And the angle is theta. RF. Okay, so since we call this L lever arm, this is perpendicular distance. And this is theta, and we also conclude that this is theta as well. So in this right angle triangle, the R is the hypotenuse, right? This is hypotenuse equal to length R, the magnitude of that vector R. And the L is opposing this angle. So we can make a trigonometric relationship that L over R is equal to sine angle between R and F. All right. So this gives us L equals R sine theta RF. So if we say that torque is equal to F times L, we can also, using substitution, L is equal to R sine angle between R and F. So this gives us some ideas that although we're using L, we can also look at this R length between the axis of rotation and this point A where the force is applied. So let's maybe extend this a little and just draw this vector force out. All right. So the significance of this FR sign of RF is we can reshuffle the terms. For example, we can take F and put F together with sine of the angle, and then just leave R out. So what is this? This is taking a component of F, right? Assuming this is our F and it is the hypotenuse of some right angle triangle. So F times sine means a component of that, right? So this F is right here, and if I draw this perpendicular line here, we can see here we have a right angle triangle. So F sine is actually this F here. Sine is this quantity. So this F is the sum of this force, which is pointing directly away from A along the line that connects axis of rotation with A and beyond. So this amount, we can call this the radial force, and this amount here, we can call it the tangential force. So the force itself is the sum of the radial component and tangential component. And this whole thing seems to be the tangential component, right? The sine is this opposing side of this angle. So this is that tangential component, F tangential times R. So this tells us the only part of the force that is effective in causing rotational conditions to change is only the tangential component. And what does the radial component do then? Well, the radial component, you can imagine, if this A is the door handle, you try to yank the door against the door and away from the door hinge, all you're doing is you're not really turning the door, right? You could damage the hinge if you just pull too hard, but you won't be rotating the door. So if this R is the door and the AOR is the hinge, and this force is effectively not causing any rotational acceleration. But this one will cause rotational acceleration. So that this force, which has part that does not cause rotational acceleration and the part that does cause rotational acceleration, can be decomposed into these two so-called radial and tangential components. So in certain textbooks, you'll be told about the radial component, the tangential component. Only the tangential component is causing the torque, which is correct. In other textbooks, you may see just torque equals force and lever arm. So you'll be required to find this lever arm length. So whichever version you do, they're the same, right? Because the lever arm length is related to the distance between the axis rotation and this point where the force is applied. And then there's a sine function. All right. So now let's discuss the torque and also the effect of choosing a different axis of rotation. So in the top left corner here, I assume this is a cardboard cutout and I pinned it at axis rotation. But axis rotation is actually not a physical point where objects are restricted to rotate around. It doesn't even have to be there. The object may not even have a point that is pinned down. The axis of rotation is a pure mathematical construct. Is very similar compared to what the origin of an axis is. So the origin doesn't have any significance. You can fix the origin of an axis anywhere you want. For example, you can say, well, I have a vertical axis. The origin is on the first floor. Or someone else could say the origin is on the second floor. Yeah, the description of positions will be different, but the descriptions of a change of position will still be the same. If you're moving up by 1 meter in any coordinate that points up with different origins, you'll be moving up by 1 meter. So that's very similar to axis rotation. So let's have a different object, and we're applying a force right here at point A with the force F1. So imagine here we have an axis of rotation in O1. So imagine what this force will cause. Well, it will certainly cause this object to rotate this way, right? But if we move the axis of rotation over here on the extension line of the force, which we have called the axis of rotation. So if I move the O over here to an O2, then imagine the object is pinned down at O2, and just pulling with force F1 will not cause any rotation. So there will not be any torque. And if I picked another point here, O3, so this will actually cause the object rotate this way. If you imagine you're pulling above this point, and that will cause the top to start collapsing down, right? So the choice of the axis rotation determines the sign of the torque, and also it determines this lever arm distance, of course, right? So the torque cannot be said as, oh, there's a one torque with a force applied somewhere in a certain direction. It also needs to be with respect to which axis of rotation. So we'll say that torque 1 with respect to O1 is positive, because it causes the rotation to take place counterclockwise, and torque 1 with respect to O2 on the other hand is going to be 0, because the line of action extends through that axis of rotation. And then torque 1 with respect to O3 will cause this thing to go the other way, so it's less than 0. So we need to be very clear with which axis of rotation your torque is calculated with respect to. Otherwise, there won't be a common ground. And this also tells you when you're doing a calculation, you should have a fixed axis of rotation. You pick that axis of rotation, you stick with it. Okay, so for those who understand what a cross product is, so I'll talk about the cross product and how to define the torque as a vector. So since we have already talked about there's a sine angle involved, and also the angle is indeed between F and R, so we can have this definition. Let's just draw an axis of rotation. There's an R vector. There's a force vector F. I will move the R vector down so that it would be a little easier. This is also the R vector. I'll draw some parallel lines here to indicate they're exactly the same. Okay, so this is the angle RF. So we know that a cross product, the magnitude of cross product, so R cross F, magnitude is RF sine angle RF, right? So since we already have this F and R and sine angle, that means the magnitude of the torque is indeed the magnitude of the cross product. So that means torque, magnitude is the same as R cross F magnitude. Because R cross F magnitude has the R and the F, the sine of the angle, so does the torque's magnitude, R and F and sine angle. So what about the direction? Okay, so the direction, we know what happens over here with this. This is O, and this is A. So if we imagine there's an object like this, and pulling at point A will cause the object to rotate counterclockwise, and that is a positive torque per our definition on the let's see, top left corners right here. Counterclockwise is positive, so this is counterclockwise, so or it's positive. Okay, so in order to create such a direction, what we can do is we can cross R with F, and what that does is, using right hand rule, you start your fingers pointing along the R's direction, and then you cross over into the X direction just by closing your fingers in this direction, and your thumb, which way does your right hand thumb point? Out of the board. So your right hand thumb points out of the board. Oops. So this is out of the board with the arrow tip pointing out. So this will be a corresponding direction that is a vector torque. Which is tau is a vector product of R cross F. So the torque is not along the F direction or even in the plane of R and F. The torque is perpendicular to R, torque is also perpendicular to F. Indeed, R and F occupy this plane, and the torque here is out of the plane, or it could be into the plane if you apply an F in a different location, or maybe change your axis of rotation. So the torque, a counterclockwise rotational effect is corresponding to a positive torque and corresponding to a torque that points out of the board. So let's see. Counterclockwise rotation. That is corresponding to positive torque. And the positive torque, which way does it point? Out of the board. And the clockwise rotation is related to a negative torque. And that will be pointing into the board with this feather tail of an arrow pointing.